Good day, and thank you for joining us from wherever in the world you may be and whatever time zone you might be in. We really appreciate you taking the time out of your busy day to spend a little bit of time with FieldComm Group in Mesco talking about the topic that we're going to talk about, which is Safe Hart. And I'm sure that we're going to be providing you with a lot of informative information. My name is Paul Sirico, and I'm responsible for marketing and product strategy here at FieldComm Group. Today's webinar, as you can see from the slide, is called Safe by Design, and it's all about developing safety certified field devices using the Hart communications protocol. So if you're expecting another webinar, you might want to drop out right now, because for about the next 45 minutes or so, we're going to be talking about Hart communications technology in all of its flavors and safety systems. We've got a great lineup of speakers. I'll introduce them in a minute, but first I have to go through and give you a little bit of the FieldComm commercial and talk to you a little bit about FieldComm Group and what we're all about. So let's do that. Okay, so I assume most of you are aware of this, but if not, FieldComm Group, we're a standards development organization. We're a member organization. Our business is primarily producing standards and also conducting conformance and certification testing for products that are developed to those standards. We have over 400 members, and in fact, this is our 10-year anniversary. We were formed back in 2015 through a combination of the Field Bus Foundation and the Hart Communication Foundation. And at the time of our founding, we also assumed responsibility for a device integration technology that at that time was in its infancy, called FDI, Field Device Integration. We have over 400 members, as I stated, and since our roots are in Hart, there's over 50 million Hart devices that are installed around the world, and it's far and away the largest communications protocol used in at least the process automation arena. While our origins were in industrial communications, our business has expanded greatly in the past decade. Notably, we're now home to the two major device integration and management technologies, FDI, and as of about 1 year ago today, the FDT technology. We assumed management of the FDT group and its technology back in July of last year, and we're working hard towards trying to come up with a single integration technology for both factory and process automation. We're also co-owners, along with 7 other companies, along with other companies that we feel are really great technologies that fall into the enterprise software arena. The first one of these is Ethernet-APL. We co-own that with PI, with ODVA, and with the OPC Foundation, and you're going to hear more about Ethernet-APL during the course of this presentation. We also own, with 7 other companies, a software standard called the Process Automation Device Integration Model. And that's kind of a bridge technology between OT and IT. OT and IT universes, and enables the communication of device data from the OT side to the IT side without any knowledge of the underlying communication or automation protocol that's being used. And that's a very exciting product as well. I mentioned that a core piece of our business is product registration services, and that's true if you happen to be an end user on the line. We'd like to make sure that you are always looking for the registered label on either whether you're buying Hart or Foundation Field Bus or FDI or FDT products. And if you're a developer on the line, we always want to make sure that you submit your devices for registration so that you can take advantage of our great services and that your product can also get broadcast in our online product registration catalog. So that's a benefit of that as well. So please look for registered products. One of the things we're also very proud of is an award that we offer every year. It's called the Plant of the Year Award. We've been doing it for 25 years or so now. And a lot of well-known names in the industry have submitted and been awarded the Plant of the Year for using field comm group technologies in innovative ways that help them really improve their operational efficiency and basically save a lot of money. And each year we have companies come forth, apply for the award, and then we publish them. We give them an award. We talk about their stories, and all of these prior awardees are located on our webpage. Please take a look at them. Maybe it'll give you some ideas on how to improve your plant if you happen to be an end user. And whether you're an end user or a supplier and you know something and you want to apply for this award, please use the link below to fill out an application form, and who knows, maybe you'll win. Today's webinar, as we discussed, is all about Safe Hart. Okay, Safe Hart was introduced into the Hart technology specifications back in version 7.9 a few years back. It requires the incorporation of some commands and other things that one of our speakers is going to speak with you about shortly. So I'm not going to bore you with the details there, but this is all about Safe Hart today. Our two speakers are Wally Pratt, who is kind of the grandfather of Hart Communications Technology. He's been working with Hart for well over 30 years and is far and away the acknowledged expert in the industry about how the technology works and how it gets deployed in products. We also have Gerhard Weiss from Mesco. Mesco is what we call a development services provider, which basically means that their business is helping you create instrumentation and products that conform with our protocols and make sure that they operate well and are developed economically, and all of those sorts of things, so that you don't necessarily have to bring in-house all of the expertise that you might need to understand the details of these protocols and things like Ethernet-APL. So if you're in the market for having devices developed, please reach out to Mesco. They're a great services provider. The format of this webinar today is as follows. To make sure that the quality is very solid, we had Wally and Gerhard record their presentations. We'll be playing them next. I'm coming to you live since the quality of my speech isn't all that relevant, I guess. But in any event, after this short intro, we're going to roll the video. Then in between the videos, I'm going to come back on and introduce the next speaker. And most importantly, at the end, all three of us, myself, Gerhard, and Wally, are going to come on live, and we're going to answer your questions. There's a chat window that you can ask questions in. Please do so, and we'll handle those questions at the end of the event. So, without further ado, if we could roll the first video and get going with the Safe by Design Hart webinar. Thank you.
Before we get into the details of implementing Safe Hart in a field device, I will take a moment to provide you with an introduction to Safe Hart and the benefit it offers device developers and end users. Let's begin by looking at what a safety system is and how it differs from a traditional control system. The plant typically has two major control functions: the basic process control system and the safety instrument system. The basic control system is responsible for efficiently making high-quality product and maximizing plant uptime. The basic plant controls are also the first line of protection and safety. The safety instrument system is a completely separate set of controls that are designed to ensure the safety of people and property at the plant. In a perfect world, it will continuously but silently monitor the plant for potential hazards. However, should a potentially hazardous condition be detected, the safety instrument system must take action to protect the plant and its people. The safety instrument system is a collection of safety instrumented functions. During plant design, potential hazards are identified and the risk levels are calculated. A safety instrumented function is then designed to reduce the risk to an acceptable level for the identified potential hazard. A SIF fundamentally consists of three major elements: instruments that monitor the process and the plant, a safety controller that looks at those signals and makes decisions, then actuators are triggered as needed by the controller to initiate a shutdown and eliminate the hazard. The key mantra here is sense, decide, and act. Communicating safe process values is essential. In other words, communication must meet or exceed a specified probability of failure, the so-called SIL level. Today, SIL-rated 420 milliamp analog communication dominates safety systems. In fact, the vast majority of safety devices are Hart-enabled. Even normal Hart communication benefits safety instrumented functions. For example, diagnostic access can further reduce risk. Configuration changes can be monitored and detected. And digital process values, even if they're not safe, can help prove the 4 to 20 milliamp comms are distortion free. Safe Hart is an upgrade to the existing Hart protocol that is narrowly focused on delivering safe digital process values to and from safety controllers. The Hart core values were the guiding principles for Safe Hart. Simple for end users and developers, works on all Hart networks, and is compatible with the tools end users already have. As a result, Safe Hart supports 4 to 20 milliamp, wireless Hart, and Hart IP. And Safe Hart procedures, operations, and the safety PDU format and calculations are the same across all networks. This enables end users to choose the best fit for their safety instrumented functions, whether it's SIL-rated 4 to 20 milliamp analog, Hart over 4 to 20 milliamps, wireless Hart, or high-speed SIFs using Hart IP. Of course, Safe Hart 4 to 20 milliamp devices are flexible, multi-mode devices able to function as a traditional Hart device, a SIL-rated analog Hart device, or Safe Hart digital signaling. Safe Hart is designed to enable safe two-way digital communication. And what we mean by safe is that Safe Hart has an exceptionally low probability of failure per hour. Safe Hart has several key features, including it is compatible with all Hart topologies. Safe communication and normal communications can share the same communication channel simultaneously. Furthermore, there's no special modifications needed for compliant Hart I/O or wireless Hart gateways. Safe Hart is the migration path for SIL-rate Hart 4 to 20 milliamp instruments. Since the PVs are already certified, really only the Safe Hart communications needs completion and the devices are recertified. It's fundamental to the whole Hart tribal chant that Hart devices coexist and interoperate with other Hart devices, and Safe Hart will work with that installed base of applications and tools. For example, during the operation of the safety controller, existing monitoring and optimization apps, diagnostic apps, can communicate with the same device. And Safe Hart devices and normal Hart devices can exist on the same network and communicate simultaneously. Pub/Sub is an essential part of Safe Hart. Safe publishing is configured once, and the devices will remember to publish that process value at those rates even after a power cycle. A powerful feature found in Hart devices is that publish and subscribe operates in its own allocated bandwidth on Hart 4 to 20 milliamps and wireless Hart networks. This protected bandwidth minimizes latency and jitter and simplifies SIF design. The safety controller are an essential part of every SIF. The controller has a watchdog timers based upon the process safety time determined by the safety engineers. A timeout will trigger the safety action. Using publish, subscribe, and safe digital process values is a simpler solution than using 4200 milliamp analog, and it reduces the possible points of failure. While developing Safe Hart, the Philcom group worked with Exida to certify Safe Hart to IEC 61508. The certification consists of two basic parts. First, a researcher performs numerical assessment of Safe Hart, and second, an independent peer reviewer evaluates that assessment to confirm its conclusions and generates the final report. The findings conclude that Hart IP and wireless Hart exceed SIL 3 by an order of 10 to the 5th, and Hart 4 to 20 milliamp meets SIL 2 requirements. As a reminder, using redundant SIL devices to achieve SIL 3 is best practice. In fact, the vast majority of the installed base follows this pattern. SIL 3 devices are simply very rare and expensive. Today, there are hundreds of Hart devices with a SIL rated 4 to 20 milliamp loop. Upgrading these to support Safe Hart is straightforward. The existing SIL rated Hart devices have their certifications with approved hardware and signal processing chain. They have a certified safe PV. These Safe Hart communication can be added. This is a firmware upgrade. Of course, on demand, Philcom Group will provide tools and test plans to help. Once implementation is complete, the certifications and device registrations are executed, registering at Philcom Group and agency certifications, for example, at Exida. Now you have a new, improved Safe Hart device that is Hart registered. This provides the user with a multi-mode device that can operate as a normal Hart device, as a SIL-rated 420 milliamp device, or a full Safe Hart operation. From there, the user can begin future-proofing their device inventories. So, we've talked about a number of different features of Safe Hart, and I'd like to leave you with a few key takeaways. Safe Hart is a backward-compatible upgrade. That means end users can leverage existing knowledge and don't need any other training. It's Hart, and being Hart, it's backward compatible with tunnels seamlessly through compliant I/O and wireless Hart gateways. Hart, with a SIL rated 4 to 200 milliamp lamp, is the overwhelming choice for safety instrument systems today. That being the case, SIL rated 4 to 200 milliamp devices only need a firmware upgrade and recertification. In addition, pure digital comms is now possible, which will eliminate analog signaling errors. Integration is seamless. It's compatible with existing host applications and uses standard FDI tools for integration. Integrating into existing DCSH, which in most cases already knows Hart, is simple and straightforward. Finally, Safe Hart allows the choice between 4 to 20 milliamp analog, wireless, and IP or Ethernet while providing consistent, simple operation across all the technologies.
Okay, thank you very much, Wally. That was a fantastic presentation. I took a couple of key things away from it that I'd like to repeat, and then I'll turn it over to Gerhard. I think first of all, it's important to understand that all three of the Hart communication protocols, Hart 4 to 20, wireless Hart, and Hart IP, are all all have Exodus certification and can be created, and therefore still instruments can be created from them. The second takeaway that I took out of this is that there's a large installed base of devices that already have SIL ratings for 4 to 20 milliamp Hart, and adding the digital channel to that is a fairly straightforward firmware update and conversion and test and registration process. So that's pretty cool. And then the third thing that I took away from this is the fact that is about hard IP, frankly, because we're in the very early days of Ethernet-APL technology. Companies are just now starting to develop instrumentation that supports Ethernet-APL, and they have a choice of a variety of Ethernet enabled automation protocols to develop from. One of them, of course, is hard IP. And because it's an IP-enabled network, you want to have a lot of security. So we've put a lot of security into the Hart IP specifications over the last several years. And if you want to use it for safety, use those instruments for safety, there's now a path to have safe, secure, high-speed, very high-speed Hart devices using Hart IP over Ethernet-APL technology. But to develop those, you're going to need to gain some expertise. Or maybe you just want to outsource that expertise to a company like Mesco. So now I'm going to introduce Gerhard, and Gerhard's video is going to come up, and he's going to give you a presentation on SafeHeart and their development services there. And afterwards, all three of us will get on the line and we'll do a Q&A session. Thank you. Let's roll the next video, please.
Welcome, ladies and gentlemen, to our webinar on developing safety-certified field devices from Hart 4 to 20 milliamps to Ethernet-APL. My name is Gerhard Weiß. I'm the local branch manager of Mesco Engineering in Freiburg in Germany. And since our local subsidiary is responsible for the focus on process automation, I'm here to hold this webinar on our field devices. Our company, Mesco Engineering, is doing tailor-made development solutions by providing customized hardware and software development based on our own design packages. These design packages are proven circuits and software components for rapid implementation of your development project, which we are willing to share with you. We also do development consulting by supporting you in the areas of functional safety, explosion-proof designs, and also industrial communication. First, I'd like to introduce with the agenda and show the situation for traditional transmitters, and then I will move over what a safety transmitter is really the basics of. I would like to show what happens if we have an Hart-enabled transmitter, and going over then for a safe Hart transmitter. After that, I will go for an Ethernet-APL based transmitter. What does it consist of, and how it can be also safety enabled. And finally, I would like to show the building blocks that we provide for having practical solutions with such devices. Initially, I would like to show the situation with field devices And generally speaking, in process automation, we have to handle high risks. We need to reduce the operational risks and prevent any damage. And for that reason, compliance with safety standard is a must. It is really required by today's industry. And a typical 4 to 20 milliamp device does handle such safety requirements, typically in hardware only, which I would like to show you later on. And for having more diagnostics information and maybe even further safety functions, additional communication channel is key. Basically, since finally nowadays anyone expect safety here. A typical traditional transmitter consists of three parts. First, the sensor, which might be any type of sensor, most prominently perhaps a temperature sensor, when we have some sensor data processing, which is of course converting analog values into digital ones, linearizing, having some calibration schemes that needs to be applied to the sensor data, and also third part, the line interface itself, which converts then back the information to some 4 to 20 milliamp signal. And as long as it stays within the valid boundaries, and if there's any failure, when we typically handle that with that Namur requirement, so that we give some failure information, which is either below 3.6 milliamps or above 21 milliamps. And we have option here to indicate at least two different types of errors. Typical properties here are we have indicate the possibility to indicate some failure situations. We have some limited hardware diagnostics in the CPU, which is up to the designer in the end. We use standard software with respect to functional safety, so we don't have any special software here. And in the end, we are signaling only that the sensor is somehow out of range for some reasons. Now, what happens if we add some safety? Some meaning here that we have some hardware diagnostics attached to the sensor, probably a check for a broken line interface or a shortcut or similar issues. Typically in that environment, we resist the temptation to give that information directly to the CPU, because the CPU is built in a traditional way, so it's non-safe, and especially we have not taken safety issues within the software into account, so we connect that diagnostic information that there's something wrong directly with the line interface. And the line interface will then be drawn either into the 3.6 or into the 21 milliamp situation to indicate to some host, hey, we have a safety fault. And by doing so, we can have a complete considered safe sensor that can be SIL qualified in the end, so typically SIL 2 or something like in that area. And the easy thing for the designer here is it's still the traditional CPU. There's no special software measurements within that CPU, and especially the software does not need to be written in accordance with the SIL standards. So if we extend that approach to a full-blown SIL design, we also have CPU built in accordance to SIL standards. So it's a safety CPU, and the software on it is also in accordance with IAC 61508-3, that is for software. Now we have a chance to do a very detailed diagnostic, not only about for the sensor, but we also can do diagnostics for the CPU itself, because we need to assume, of course, in the end, that the CPU has also some safety issues, maybe a RAM cell got corrupt or similar things. We do additionally some checkings for the line interface itself as well, and in the end we can indicate this safety situation that something went wrong in the end, again by using this 21 or 3.6 milliamp special indication. Please note, in the very moment when we figure out that there is some safety issue here, we are no longer able, because of that scheme, to indicate what the reading of the sensor is, even it is still available. And that is a major issue of the approach. But wait, what is a safety core? This is more than just a single channel CPU with some internal diagnostics. We have complete internal diagnostic sets in such a case to assure that we are in accordance with 61508-2 of safety standard. For that reason, we have to have an external test equipment, which is mainly an external window watchdog, to ensure that there is some additional hardware that works in parallel to the internal diagnostic and brings the system into a safe state if anything goes wrong within the internal CPU. And of course, such a safety core has to use a software in accordance with the safety part of safety standard 61508. And that software ensures that it is at least to some extent designed and developed in an fashion that it is likely to have less errors than in a standard software. Yeah, to overcome this issue, actually here comes for the first time Hart into the play, and at this point we are still talking about Hart, non-safe, not on safe Hart, but standard Hart. But now we have this additional Hart information modulated on the line interface. And despite the fact that we now probably see that there is some local issue, something is degraded in our sensor, and we go into this failure information status where we no longer can indicate the process variable, the primary process variable on the analog interface, but we still can now show within the Hart communication protocol what is the value of original process variable, and also can give some diagnostics, for instance, that we have an issue found within some memory cell or something similar. And although we now have a full-blown safety system with diagnostic information, please keep in mind the safety itself relies on the 4 to 20 milliamp still. So the safe state signalized to the remote host is still the analog interface. It is not the Hart signal. The Hart signal gives you additional diagnostics, so the Hart signal is still considered here being non-safe. So in this picture, which looks at first glance completely identical, we have a different situation. We still have a 4 to 20 milliamp, and we still could signal safely here a safety situation, so we could indicate a safe state. But we have not only the Hart communication protocol, but we have an additional thing here, the safe Hart implementation, which is located now on the safety CPU, which is a topmost layer that is able to communicate to some remote site in a safe fashion, telling, okay, we have some diagnostics issues, and we have some safety situation that goes via a black channel through to the Hart modem, and that is transmitted to the remote site, giving you the information in a safe fashion by using the concept of black channel. Now, wait, what is a black channel? A black channel is a scheme where we transport safety relevant information through a non-safe part of the hardware. And so traditionally it is located together with a non-safe communication scheme, so that we have non-safe data that use some network, and we have safe data that now also is allowed to do to use it the very same networks. So we need to have additional safety mechanisms which are implemented on the application layer, as you see here in these yellow in the yellow parts here. And these safety layers that implement continuous retransmission and timeouts and other measurements to identify any broken communication infrastructure. In order to be accepted as black channel communication, it needs to comply either with the 61784-3 standard communication scheme or to the 62280, and in that case it can be considered a safe communication, which in the end goes through some odd channel, which in the end is not assumed to be a safe transmission otherwise. Okay, now that we've seen that we can do functional safety with a traditional analog 4 to 20 milliamp approach, why would we go any further? Yeah, we have a simple interface, whereas easy debugging of a line in the field, we just need a multimeter. We have very low energy demands, and these devices are well known in handling. And so that's in the end, it's easy devices and easy handling. The problem with them is the access is always local, so you can go to if you want to know more details about a device, you need to really to go where it is and have some more checks. So the real internal variables it's very limited what they provide to the outside world. And of course the energy budget is very low, meaning you can hardly do things that require even a little bit more of energies, and access of device and remote debugging, that is really limited. A field update, for instance, for such a device is almost impossible because of the low speed of Hart, if there's Hart at all. And just set it here. So to overcome these issues, there have been quite some efforts to have per service connectivity of Ethernet bringing to the field by the definition of Ethernet-APL. It is a single wire pair, so most of a 4 to 20 milliamp cable installation can be reused. We can bring a power also, not only communication, but also power of approximately half a watt into the explosion zone 0. And of course, we have full duplex 10 megabit per second for 200 meters per for a 1 kilometer trunk. And that comes in the end with a fully transparent standard Ethernet, not at a high speed, of course, but 10 megabit is, of course, some a much more of speed than, for instance, a, a plain hard interface. So how is this done? The signal is finally transcoded in a 3-bit way, so we have 3 bits coded at once, having this 4B3D transcoding, and that removes any DC offset, because DC, of course, is the power supply. And we're reducing the baud rate by down to 7.5 megabit rather than with 10 megabit, which also relieves us a little bit when it comes to performance on such a long path. Just as I said before, any DC offset is the power supply, so we have phantom power feeding, which is called power over data link, and that goes directly in a local power supply, and where we have definitions for various classes, and the first 3 classes defined for this. Even for higher classes, there are higher classes definitions available, which are not intrinsic safe. So we have these 540 milliwatts for class A and 1.17, 1.11 class B, class C, which are dedicated for zone 1, zone 2. Of course, communication in such a system is somehow more complex. We are communicating with Ethernet, meaning it's TCP/IP. It is other protocol families on top of that, and so we need some protocol stack which is typically not available as a safety software. So for that reason, we have a dedicated communication CPU. We have a PHY, we have a line interface including the power sourcing, and then we have a local safety CPU which is directly connected to the hardware diagnostics and the sensor. And here we apply this black channel communication once more, and we can now use any safety layer for any communication protocol combination that is available or prominent in the outside world, where Ethernet is already the standard communication scheme. So what does that mean for our Hart-oriented world? We now have Ethernet, and originally Hart was not designed for Ethernet. So what do we do now? Yeah, there is already a solution on this issue, which is already there for more than a decade. That's Hart IP, the very same protocol based on top of TCP/IP, and that hard IP actually needs now a safety layer, which is the safe hard, and in the combination it resembles safe hard coming from the safety CPU doing a seamless black channel communication to the outside world. And we have now the very same solution as we have had with our safe hard approach for a traditional analogous device, with the benefits, of course, of the much higher power and the much higher speed. Of course, this approach is not limited to safe hard. We also can use the scheme of Profinet with ProfiSafe, as you see it in this picture. Here we use Profinet as underlying protocol on the communication CPU, and here the safety layer of ProfiSafe is implemented on the safety CPU. And in that combination, we can now communicate to an outside world which is built around Profinet ProfiSafe. So, what is the conclusion of Ethernet-APL system that I've shown you? Safe hard can be used to extend your hard-based design for a safety environment. You can use it in SIL2 and SIL3 applications, and you can, in that case, reuse the existing hard infrastructure. So how would you do that in the end? You would use these components that are available in our design packages. For instance, the COM CPU board with the PHY and the portal interface, including a power supply. That is one board. We have a safety CPU, that's the other board. You would adapt your sensor with your hardware diagnostics to that board. We would provide you a development for such an integrated system to get it into a real device in the end. And of course, for taking care about functional safety, we have to take care of a well-defined development process, which is, for example, here showed as our validated development process. Here is an example of our development boards, some typical boards that we have for other purposes, and in the background you see the baseboard just for starting developing. Here you see a first 3D rendered image of our Ethernet-APL board. We do, of course, have also real examples, but they are still in a different form factor, and we're actually about to have that here in factory. And here you see a picture of a safety CPU board, which is under preparation for the moment. So finally, here's our overall offer. So what do we provide? We provide analog, digital, and low power designs in hardware. We do embedded functional safety and measurement in software. We are very keen in field-based safety communication, industrial Ethernet, and of course for available for functional safety development around 61508 or 13849, but not limited to these two standards. And we of course do some FMEDAs in that area, but we are also available for intrinsic safety, regardless if it's ISCX or ITX or it is FM or CSA qualified. So our services are requirements engineering, it is development of explosion protected, intrinsically safe sensor, actuator or control system, development of functional safety automation components, connection of process controls with fieldbus, Hart, APL, or SPI, or power supply over bottle, proof of conformity, of course, with various standards in the intrinsic safety area and also in the safety area. So please contact us in our headquarters, of course, in Lörrach, or any of the local subsidiaries which you would like to prefer. Thank you.
Okay, thank you, Gerhard. Thank you, Wally. These were tremendously informative presentations. I hope the audience feels the same way. I know I learned quite a bit today. We do have a few questions that we prepped ahead of time, and I'm hoping that you all will enter some questions into the chat bot as we are going through some of these initial questions. So the first question I have is for Gerhard. And Gerhard, can you kind of get into? I think you said that you need two separate CPUs to develop a system. Why do you need two? Isn't it possible to handle the safe and the non-safe actions on a single CPU, or what's wrong with that?
Yeah, theoretically, you could indeed handle that in a single CPU, but in practice, that is quite some effort. Yeah, you need to know you must validate your software that with non-safely written software that comes from some third party, that this software does not harm the rest of the system and brings it into a non-safe situation, for instance, by a dangling pointer and things like that. And having that separated is really a thing that is very complex to show. So if you're doing large quantities, then this effort might be interesting to do so. But for typical volumes, it is quite often easier to have two separate CPUs.
Got it. Got it. That makes a lot of sense. Thank you for that explanation. Wally, I have a question for you. I know you mentioned this in your presentation, but I think it's important that you can reiterate it a little bit. You mentioned that there are already many Hart devices, registered Hart devices that have that are still certified 4 to 20 milliamp. Obviously, what would be an abbreviated process? What does a supplier have to do if their device is already still certified? What do they have to do to make the Hart digital communications channel certified?
Well, those devices have an advantage because they're already have the entire sensor processor chain certified. And they are already taking a digital PV and convert it to a current loop, and that entire chain out the current loop is certified. So what has to be added onto that is the safe Hart communication. And that is principally a firmware upgrade and then documentation on things like, what's the probability of failure of the modem chip they're using and a few other things. So these people have a real leg up to get into the safe Hart game pretty quickly in my mind.
Okay. Okay. Good. Good. We got a few other questions that are coming in. One of the questions is SafeHeart implemented in any plant worldwide on a pilot basis yet? And the answer to that, to the best of my knowledge, is no. The specification just came out a couple of years ago, and as everybody is aware, the process of actually developing, changing a device, going through all the certifications, all the SIL certifications, takes some time. So, but there is tremendous interest in this technology. We get a lot of questions about it from our suppliers. So, I'm confident that there's work going on, and that over time you'll start to see these things appear. Question for a general question came in about MESCO, and the question is, let me find it here. Does MESCO only do complete development for customers, or are you also support other hardware or software related services?
No, we have different kind of projects. So we do hardware development projects only, we do software development, and we do complete product development. So it depends on the customer relation and the collaboration with the customer, what we do. So yeah, but we do both, and we bring it from
Okay.
the requirement back up to the certification stage.
Okay. Another question here. Gee, I don't know. How much power is typically available on an explosion-proof Ethernet-APL device?
Yeah, that depends a little bit for which zone you are going for, but the most demanding is of course zone 0, and here you have these mentioned 540 milliwatt, but it takes quite some power already from the internal CPUs. So the discussion is, of course, how much power is left for your sensor and the environment. And it is quite promising that we can provide you for your sensor application up to 250 milliwatt, which is quite a different thing that from what you actually see.
Okay. Another one is, what's so special with black channel communications? What's the difference between that and traditional communication schemes?
Yeah, actually, it's this black channel communication that relies simply on its own properties to recover from errors going through the traditional communication scheme. So, if you, for instance, have some standard IP communication where you could have missing packets and things like that, um, the overlying black channel safety layer will take care by continuously repeating at a high speed the information and having a timeout on the other side, so that it looks to the remote side as if we just have a clear direct connection to the safety information, and the complete underlying protocol is not really a growing part anymore.
Okay, great. We've got one more question that I want to get to, and we're about 2 minutes over our allotted time. So I'm going to ask that, and then we can wrap it up. And this one has to do with IEC 61508. I'm looking down because I had to read those numbers.
Mhm.
Does the Hart Safety Communications layer meet IEC 61508? First of all, what is IEC 61508? Maybe then you can
IEC
answer for us.
65108 is an umbrella for all the safety stuff. And
Mhm.
in the last couple of years, they've added one of the documents to it had to do with the actual communications as opposed to the overall safety stuff. And so these are really the international standards that you have to meet. And
Mm-hmm.
so when we worked with Exida did pretty exhaustive calculations and assessments to confirm that it meets all of the requirements of 61508, as well as met all of the reliabilities. The probability of failures are appropriate for that. And so that's the testing and regimen. And how we did that, it's a you know that's a whole we did a whole survey, I mean a whole presentation on that. So I don't want to get into all that, but yeah, we've been through that, and Exeter helped us.
Okay, great. Okay, three final things. First of all, if you are a supplier in a development role and you want to learn more, please take a look at the Hart specifications. We have tools that you can purchase. You can read about the Safe Hart in the specifications. There are a couple other webinars that we have done on this topic. And obviously, you can reach out to MESCO and start talking about your design needs. Number two, if you are a supplier and you happen to be in a customer facing role, please start talking to your customers about incorporating SafeHeart instrumentation into their facilities. It's a great feature, and it gives you kind of two channels of safety basically. Between the 4 to 20 milliamp and the digital communication standard, and that sounds pretty good to me. And might be able to sell some more instruments. And finally, if you are a end user and you're on this call and you want to learn just about SafeHeart, I hope you found enough information and enough content that you can have an intelligent conversation with your suppliers and start asking them when are they going to be providing safe Hart enabled products so that you can buy them and install them. So without further ado, thank you to the speakers. Thank you to our backstage staff and who are kind of running the cameras and making sure that everything worked fine. I hope you found this interesting. It will be recorded and you can watch it later, and we'll certainly let you know how to do that. So thank you very much. Have a great day and a good summer. Take care. Bye.
Thank you.
Thank you.